This is our work titled Amortized NeuralSDF and Mesh Collision Detection for Robotic Contact Simulation. We propose a novel amortized NeuralSDF and mesh collision detection framework that is accurate, computationally and memory efficient, and capable of category-level generalization. The video shows simulation examples, visualizing collision detection results, including contact points and contact normals. The colored objects use SDFs as their collision geometries, while the gray objects use meshes. Our goal is to develop an accurate and efficient collision detection between non-convex objects. For accuracy, we adopt NeuralSDF as our SDF representation. For efficiency, we introduce learning-based amortized optimization, replacing conventional iterative optimization. Our amortized model predicts a contact point for each mesh triangle. The input is the vertex coordinates of triangle, and the output is the barycentric coordinates of the contact point. We design a loss function based on the KKT optimality conditions of the original optimization problem, which minimizes the SDF. This loss enables unsupervised learning. Our network consists of a shared MLP and an auto-decoder architecture. These are the simulation results and comparisons. The first scenario is a mug and rack hanging scenario. A Franca with a parallel gripper picks up the mug and hangs it on the rack. Our framework achieves stable and efficient collision detection, while the baselines suffer from slow or unstable computation. The results on the left demonstrate category-level generalization to unseen objects enabled by our auto-decoder architecture. The second scenario is a bottle and holder placement scenario. The robot picks up the bottle and places it into the holder. Our framework detects the contacts stably and efficiently, while the other baselines suffer from slow computation or sometimes fail to detect contacts resulting in penetration. The generalization results are shown on the left. The third scenario is gear-to-gear meshing, a challenging contact-rich task due to its complex collision geometry. Our framework provides stable and efficient computation, allowing the gears to rotate smoothly, while the baselines show slow computation or intermittent contact and sticking movements. The last scenario is a bolt and nut assembly, another contact-rich task. Our framework provides stable and efficient computation, while the baselines suffer from slow or unstable computation. Even with VoxelSDF representations, they fail to detect contacts because their resolution is constrained by memory consumption. Thank you for watching our video. For more details, please check out our full paper. The link is in the description below.